can stop there. That's sort of enough. That's what the syllabus mandates that I have to show you. But I was thinking about something this morning, and another way of solving this, a third way, and it gave me a problem. It came up with an answer I wasn't expecting, and so I thought maybe you'd be interested in it as well. So I'm going to show it to you. Our three approaches are, number one, t-results, number two, auxiliary angle. The third one I'm going to call by identities. You'll see why in a second. Okay, so if you've got subheadings on each of these, make another one. I'm gonna leave that there. So, this is number 3. Okay. So the question I'm solving, sine plus cos, right? Usually our strategy with these kinds of questions is to bring it down into something simple enough that I can solve it with other techniques that I know. Okay? So we've brought it down to t's, or we've brought it down to one function. But you know, this is not the only way that you can bring it down to one function you can solve it, right? Because sine and cos, they have this relationship with each other. That you can turn sines into cosines and cosines into sines if you squeeze it the right way. Okay? So do you remember, based on the Pythagorean identity, right? Sine squared plus cos squared. If I wanted to turn this cos into something in terms of sine, what could I turn it into? Do you remember? We used this when we were differentiating the inverse trig function. It starts with a square root, and what's underneath? 1 minus sine squared. Do you remember that? Okay. In truth, it's plus or minus. It's plus sometimes for different domains of cos, and it's negative sometimes. But as you'll see in a second, it doesn't matter which one we pick. So let's just see what happens as we approach this and sub this in and what happens. Okay? So I've got sine x plus this square root business. Now on the face of it, this looks good. Okay? Because you know when we were doing equations reducible to quadratics, and you'd have like sine squared plus cos squared, and you want everything in terms of one kind of function. And this is all in terms of one kind of function, right? So this is good. So how can I simplify this? What would you suggest? What would be my next step? I'm eventually going to have to square, right? But I don't think I should square this line. Why not? Why is squaring this going to give me problems? Yeah, this square root's going to give me, it's going to hang around. Even after I square this left-hand side, you have a squared plus b squared plus 2ab. So that's a problem. If you remember, we had this kind of issue with the locus questions, okay? You have distance equations, you've got to move one. So I'm actually going to swap their places. I'm going to move that 1 over, and I'm going to take the square root over the other side. That's a minus sign, okay? Now I'm in a position where I can square. Okay, so what happens to my left-hand side? I'll get sine squared minus 2 sine x plus 1, and then I've just got 1 minus sine squared here. Okay? By the way, this is why you can see it didn't matter whether I picked plus or minus the square root, because I squared anyway. Okay, so no problem. Now what? This is an equation reducible to a quadratic, right? So I've got a plus 1 on both sides, so let's get rid of it. Then you've got a sine squared here, so I'll kick it over the other side. And this should start looking familiar. Very, very similar to what we had before, right? Except we had tan of x on 2 at this point. I can still divide through by 2. That's a bit cheap, but you guys get the idea. And then I can factorize, right? Sine x minus 1. Okay? Now at this point, everything's looking nice and sweet. The algebra wasn't too hard, and I haven't even had to muck around with the domain, because it's just 0 to pi on, sorry, not pi on 2, to 2 pi. And I don't have some weird x on 2 thing, or x plus pi on 4, so this is looking good. Okay, let's solve it. You've got sine x being equal to 0 or 1. Okay, so you break it apart, and you say, when is sine x equal to 0? You tell me. Just regular old sine x in the normal domain. 0, 2 pi, and in the middle, right? Because this is what it looks like. Okay, so I have 3 solutions here. 1, 2, 3. Okay, so far I've got 0, pi, 2 pi. Okay, I need a new pen. Hold on. Then you do the other part of it. Sine x is equal to 1. Okay, and that's an exact value. That's pi on 2. Now, at this point, you might not raise any questions if this is all you had done. Okay? But we've already solved this question twice. And something's gone wrong, hasn't it? What's gone wrong? I have an extra solution. This guy's sort of snuck in. Okay? Now, sure enough, you can test all of these results. For instance, if we come back to our original equation, okay, and you put in pi, you'd put in, what's sine of pi? Sine of pi is 0. And what's cos of pi? That's -1. Hold on a second, something's gone wrong. So, if you knew, okay, something might be going on here, you could test and you could show up. Sure enough, pi is not a solution. My question to you is, what was wrong? What was wrong with our approach? The algebra is okay. These solutions are okay. So how did an extra solution creep in to this approach where it didn't in the previous two? Does anyone have any ideas or suggestions? Why might I have an extra solution? I cancelled stuff out? Oh, that's interesting. I did cancel stuff out, but usually when we cancel stuff out, we get less solutions, not more, right? Like if I gave you this, okay, and you cancel stuff out, you divide through by x, you get one solution, but really there are two. So cancelling usually reduces the number of solutions we have. It doesn't add them. It's a good suggestion. It does change the number of solutions, but the wrong way. Any other ideas? I squared it. Okay, so this line here. Wait, hold on. Yeah, this line. I did a couple of steps. Why would squaring it give us problems?
The root was literally negative, and then we squared it gives us extra solutions.
Okay, alright, now, I was thinking about this morning because I was really sort of banging my head against the wall on why it was there and why I could show it was wrong, whereas, you know, all the rest of the solutions are fine. Okay, so maybe you can rule this solution off, put like big red writing over it that this is not a good approach, and I'll justify why in a second. And